5-day GIAN course on non-invasive fault diagnosis of propulsion motors in electric vehicles. So today is second day of GIAN course today. So you know the main key categories of failure of electrical motors: bearing failures, stator winding failures, broken rotor cores or end rings in case of induction machines, high air gap, eccentricity and unbalanced magnetic pull. So this may lead to the consequential rotor or stator problems. And yesterday also we have seen sir has discussed so many this type of failure aspects, especially eccentricity, fault diagnosis. There is various ways, there is invasive or non-invasive techniques. So also discussed signature analysis, current signature analysis, and also given some of the activity for you, different methods available for determining the or evaluating the eccentricity, and also in the lab sessions also given briefly the number of specific permeance analysis, also some of the empirical relations also shown, and how we can get the different bands in that frequency spectrum, and also given hands-on experience for ANSYS, using ANSYS software. So today you have an interesting topic, so which is very essential for further research aspects also, challenging aspects. So that is introduction to machine learning methods for detecting air gap eccentricity faults. So Professor Ilampati is the key resource of this GIAN course. Sir will be doing that. So hands.
Thank you, sir, for the excellent review. You have reduced my work to do the review. Thank you so much. Good morning, one and all. Hope everybody had nice rest. A relaxing evening yesterday, and nice to see you all. So the main intention of this session, or today's, is going to be to get introduced to some of the elementary or some basic machine learning methods that can help detect eccentricity fault. I must use the word machine learning method with some caution, because one of the techniques I'm planning to present might not be considered as a machine learning method, to be honest. Okay, but nevertheless, it's a good starting point for us in this course, and as we go through the course, you will go deeper into different techniques, and you will appreciate the merits and demerits of different approaches. Okay? First, let me do a quick review of what we did yesterday, so it should not take more than a few minutes. And then I will highlight what are the limitations of conventional fault diagnosis schemes, and why machine learning methods have been gaining prominence of late. The introduction itself is not too elaborate. It's a single slide introduction. I just want to give you a picture of what machine learning methods typically means, and then we will get into the actual meat of the top day, which is diagnosing eccentricity fault using some techniques, okay, machine learning algorithms. Okay, so to quickly review for those of you that missed yesterday's morning session, eccentricity is defined as a non-uniform distribution of air gap due to an offset between the center of rotation of the motor and either the center of stator or the center of rotor or both, which is what we call as mixed eccentric condition, right? Static and dynamic eccentricities are the two types that we learned yesterday, and typically they occur together. So mixed eccentricity is what we can expect in a practical system. Then I talked a little bit about different approaches that are traditionally available to diagnose eccentricity faults. They can be broadly classified as invasive techniques and non-invasive techniques. Invasive techniques use sensors inside the motor, okay? And non-invasive techniques use sensors outside the motor. So they are all sensor based. Where the sensors are located makes the difference. The main challenge with invasive techniques, even though they're accurate, they're prominent, they're widely used, is that modern machines are becoming more and more power dense. That means the area or volume to produce the same amount of power is shrinking. So the space to accommodate sensors inside the motor is a challenge. One of the popular non-invasive schemes that I presented yesterday is a motor current signature analysis. So in motor current signature analysis, we carry out what is known as a magnetomotive force permeance analysis to predict the harmonic frequencies that would appear in the line current spectrum. And then I also talked briefly about how one could quickly model a faulty motor using finite element tools that are commercially available. Okay? So the idea is, by doing these things, modeling, you can extract line current data as if you have access to a physical setup. And once you have the line current data, you can do Fourier transform or carry out spectrum analysis or different types of signal processing to detect different frequencies and check whether there is a fault or not, right? So everything looks good. So what is the drawback of in the approaches that I presented? Invasive approaches, of course, the main problem is they are invasive in nature. That means to build a machine with sensor is going to be a little bit more challenging, can be more expensive as well. For MCSA, motor current signature analysis, one of the major drawbacks is its sensitivity for operating conditions variations. For example, if there is a variation in supply voltage, or if there is a variation in a load, how does this impact the harmonic spectrum can affect diagnosing faults. But what I want to emphasize is the last bullet. See, in any practical machine, we know that there is always some degree of eccentricity, right, by default. There is no ideal healthy machine, right? So if you do MMF permeance analysis, what you expect is you expect a healthy machine spectrum to be like this. There is a fundamental, the fifth harmonic to be backward rotating, the seventh harmonic to be forward rotating, and so on and so forth. And when you have mixed eccentricity, you expect 0.5 plus and minus around the fundamental sideband frequencies. But in a practical machine, when you go ahead and collect line current data, which is line fed synchronous machine, this is how the spectrum will look like. Okay, so I'm not saying this is how always it will look like, but at least when I collected and ran FFT, I got this spectrum. The reason being that the machine already has some eccentricity, right? Mixed eccentricity in it, some small degree maybe, I do not know. And consequently, you will see different harmonics even in healthy spectrum. Right? So it's very difficult to say what is healthy, what is faulty using traditional current signature analysis if the motor's assembling and manufacturing is not to stringent specifications. So this is a lab grade motor, and this assembled by graduate students working for research purposes. So the assembling techniques might not be very good, right? So probably when we assemble it as a healthy motor, we have introduced a higher degree of eccentricity. Like there is no way to verify that. So these are things that can impact motor current signature analysis. Another aspect is voltage unbalance, voltage harmonics that can impact. So what I'm trying to say is, even though motor current signature analysis is widely used, it is still not immune to many problems or many challenges. And with the advent of extremely high computing capabilities and advent of communicating sensors, or sensors that can communicate wirelessly, Internet of Things basically, there is a remote chance that we could collect a lot of sensor information, share it to a high performance computer, and use a machine learning model to train and develop models. Okay, so the scope is now possible, and that is why we are trying to explore machine learning methods. Okay, so basically what we are trying to do is, as human beings, when we look at this frequency spectrum, it is hard for us to discern. So we are trying to take help from some a different person or a different entity, in this case a machine learning model, which could probably see some other pattern that we are not able to visualize, and it's able to detect and diagnose. Okay, so the whole idea of machine learning is something very simple, as captured on this slide. Let's consider all the sensor information as our raw data, and for the purposes of the first few algorithms, let's assume that we know, when we collected the data, we know whether it came from a healthy condition or a faulty condition. So the ground truth, which is also called as the label, is known to us. The ground truth is known to us. So using the ground truth and using this raw data, we can actually generate training data, and we can create an algorithm and create a mathematical model using the training data and the ground truth. Okay, we can say that if this is the data I give it to you, this should be the expected output. So I feed that information into a black box. What is the goal of doing this? The goal is, after I do it multiple times and I'm confident that I have trained my black box, if I give an unknown test point to this black box, it is able to predict whether the test point is going to be a healthy or a faulty case. Prediction can be done in many ways. If it is healthy or faulty, the machine can do a coin toss, and it can say it's going to be, if it's heads, it's going to be healthy, if it's tails, it's going to be faulty. That is one simple way of predicting. But that is not what we want. We want a prediction which is a bit more mathematical, bit more accurate. So we need to have higher probability of success, right? So we want to go towards 90% or greater than 90% success of prediction, right? So that is our intention. So ideally speaking, given a test point, this black box which we have trained and developed should be capable of saying whether the test point falls under healthy category or faulty category. So this is the first objective. We can develop subsequent objectives as to, can the model estimate if it is faulty, can the model estimate to what degree of fault is existing in the test point. So that is another layer of machine learning problem. Okay, but we will not go into that today. Maybe hopefully by Friday we will be familiar with these things, that we can explore that aspect as well. Okay, but for now our goal is something simple. Given a test point, I want a black box, a machine learning model, to say whether this would be a healthy test point or a faulty test point. That's all we are trying to do. And this is the objective of machine learning models in general, as an overview. Okay, okay, so now that we have done a little bit of talking, I will start with a simple activity. What I'm going to do is, I'm going to show a slide. The slide will have two tables. One table, which is on the left hand side on the slide, has some test training data and label. You are going to look at the training data and label. So you will have 30 seconds, less than a minute basically, for you to look at. And then on the right side, you will have a test point, and you will have option to predict the label. Okay? I want you to do this exercise, but without talking. You are just going to do it just by observing all by yourself. So you are going to look at the slide, forget everyone else that is in the class. Imagine you are the only person in this room. And then look at the slide, 30 seconds on the training data set and the labels, and then go on to the test table and check and come up with predictions. That's it. You can be right or wrong, doesn't matter. Okay? Okay, so the activity starts now. Okay, 30 seconds is over. So if you have to predict the labels, please do that. Okay, 5, 4, 3, 2, 1. I hope everybody is able to predict the label of these test points. What is really happening is this test point is actually not a test point. In theory, I mean, in theory it is, but in practice it is not. If you really look at this, the test point exactly matches with one of the data points of the training data set. Now, one key aspect I want you to be aware is in machine learning models, we do not want the model to memorize and come up with conclusions. What I'm trying to say is, if the table is given on the left hand side, if I have some memory ability, if I say that if data is 7, label should be P. If data is 24, label should be C. If I can train my computer to save that in memory, then when a test point is given, it will check, is the test point given in my list? 7 matches, yes. What was the label? P. Okay, I will assign. So that kind of assignation is not called as machine learning. Okay? So it is a memorization, and usually we have a name. We want to avoid such circumstances. We do not want our training model to be exposed to test data, honestly. Okay? So the test point should be completely unseen by the training data as much as possible. The problem with a memorization model is, if the computer had just memorized, or if the model is built just by memorization, if there is another test data where the values are different from the training data set, then a memorized model cannot predict accurately. It may still give some labels, but the accuracy will be severely compromised. Okay? So what I want you to do now is go look at the table again and see if you can predict the labels for the new test data set I have shared, and let us see what you come up with as predictions. Okay? So does anybody want to go for the first test data? 36? C. Okay. Yeah, many people say C, so I'm writing it C. 93? C. Okay. 54? C. Everything is C. So this should be CC. No, I should not be in a rush. What is 71? P. Why P? We will check. 23? P. So some of you might have already learned, or you have already created a model in your head based on the training data set. So what I have done is I have created a label for prime number and a composite number. So if the number given is a prime number, I have given label P. If the number given is a composite number, then it's label C. So all I have to do is I have to take a test point, check whether it's a prime or composite number, and then assign the label. So that is the model your brain would have processed. So machine learning in essence is trying to mimic our way of thinking. Okay? So this is why sometimes you will also hear artificial intelligence being used in synonymous with machine learning techniques, because we are trying to generate human behavior in machines. Okay. If you have predicted this, and if I know these are my exact labels, then this prediction accuracy is number of labels predicted correctly. So if I know my ground truth, and if I say this is C, 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 P, P, then the accuracy of prediction is 100%. Okay. It may so happen that you predicted like this. So you have got 1, 2, 3, 4 correct, one of them incorrect. So the prediction accuracy would be 4 out of 5, which is 80%. Okay. So the terminologies are clear, right? So that is how we will quantify the accuracy of prediction. How many we could correctly identify compared to our ground truth. So we need to know this to be able to check. So in reality, what would happen is the ground truth might not be available. Right? So when you are given a data set, and if I ask you to say whether this is coming from a faulty motor or a healthy motor, you cannot say that, okay, I am predicting healthy, can you please verify? I have no idea, right? So we need to come up with a means where our accuracy of prediction is high enough, and we are confident of our model of this accuracy of prediction. That even without ground truth, we can say with confidence, with 85% confidence, with 90% confidence, that the predicted value is correct. Okay? So this is the problem. So machine learning output is always going to have some kind of degree of confidence, saying that, okay, I'm saying 95% confidently that this is going to be a healthy set, or this is going to be a faulty data point. But there is always chance of it going wrong. Okay? So you will have to quantify, or you will have to generate measures to quantify the inaccuracies. And there are many measures. We will not go into all those details today, but I'm just trying to give you a broad picture. So when you are trying to predict without knowing what the exact ground truth is, you can only predict with certain degree of confidence. You can say I'm 100% confident, but that is very rare, right? Because you are never certain. Okay, so this is the basic idea. Now, an important terminology I want you to be aware is what we call as feature. Okay, so the training data in the table given on this slide has only one number. So we have what we call as one-dimensional features. So there's only one value for the training data, right? We call that as a one-dimensional feature. And this entire set of rows of features, or this entire set, is called as a training data set. So training data will have feature, label. So this is label, this is feature. And you will have multiple rows of features and labels put together. That is the training set or training data. Okay. Now the feature need not be just one dimension. Okay. So I will give you one example. I will give you another. This is again an activity for you. So I am giving it training data where there are two features. The two features are two numbers separated by comma. And then there are labels. And if I give a test data, you can think about it. And I'm confident that most of you would have figured out the model for this. Some of you might not have, but basically what is 3,7? So if I plot it, you will understand it easier. So 3,7 would be 3, 7 somewhere here, and then 2,4 is somewhere here. -2, -6 minus 2, minus 6 is somewhere here. And then minus 9, minus 15 is somewhere here. So like that. So what I'm saying is everything here is called as Q1. Everything here is called as Q3 label. Okay. So that is what the training data suggests. Right. So here the feature is not one number, but it is two numbers. So we call it as a feature vector of dimension 2. Okay. It is a two-dimensional feature vector. Okay. The training data is made up of putting together the feature vector and an appropriate label. Okay. And because we know the ground truth which we are using to train, this type of machine learning method is called as a supervised learning method.
Ground truth is known.
Ground truth is known while you train. So for any training model, you know the ground truth, and therefore you have a supervised learning method. Okay? Okay, so now comes the first question to you all. So I hope so far whatever I said makes sense. These are, I wanted to introduce you to the terminologies. So something called as feature, and feature is a vector. It can have multiple dimensions. It can have dimension 1, 2, 3, 4 up to infinity. There is a label associated with that feature vector. Usually it's only one value. A label is just one value. It can be a number. Usually it's a number. You can give 0 or 1. Rather than saying Q1, Q3, you can say 0, 1 like that. And this is known ahead of time, and we use that information to train our model, and therefore we call that as a supervised learning. So somebody is telling you, yes, this is right, this is how it should be classified, right, ahead of time. So that is that supervised learning scheme. Okay. So the first question is, let us consider from our, so this entire focus is on electric machines condition monitoring, right? So we are always going to think along those lines. We are not, I am not a machine learning scientist. I am not a mathematician or a scientist that has worked on machine learning side. But what I am trying to do is use these principles and apply it to the field of my choice, which is condition monitoring. Therefore, my goal is to classify whether a given test point is coming from a healthy motor or a faulty motor. Okay? That's all I'm trying to do with the machine learning approaches I'm introducing. So let us consider we have a sensor. What is a sensor? Let's say the sensor is outside the motor. Could be a current sensor, vibration sensor, temperature sensor, or an audio sensor. Could be anything. And it is giving us some raw data. Okay, so let's say for simplicity's sake a current sensor, a current probe, it gives line current data. So you all have a clamp on current probe, you would have seen it. So we are using it to collect line current data. So the first question to you is the training data that I am showing here, is it same as the raw data that is collected from the sensor? What do you think? Okay, no is one answer, yes is one answer. There are two answers for sure. Why? Why do you think yes or no? That's the...
Sometimes the noise may have added while sensing that
Current sensors may pick up the noises. High frequency noises also.
Sometimes that sensor output coming with some offset values.
Okay. So there may be some additional information you are saying. So that is not necessarily used for training purposes. Okay. Any other answer? Does anybody think yes, training data is same as raw data? Okay, raw data may consist of only features, not the label, right? So that is good. So when you collect data from a sensor, it will not tell you whether it comes from a healthy machine or a faulty machine. So the label is missing. So this is a fundamental difference. The other difference, yes please.
Analog to digital conversion
analog to digital conversion might be needed. Okay? But what I'm trying to say is, the problem with us is we are being trained to think like engineers, right? So we have been trained since BTech first year to always think from an engineering perspective. But once we enter data domain, there is no physical significance to the numbers that we are seeing anymore. Okay? We don't have to associate. They may have some meaning, but they may not even have any meaning. What I'm trying to say is, the feature may be something that we generate out of the training raw data. They are not directly line currents. You can take, say for example, I will give you a very crude example. So you all know wheat, like WHEAT, wheat, right? So let us consider that as a raw cereal. You all know semolina, suji, everybody is familiar. Rava, suji, okay? So that is, what is rava, what is suji? It is also wheat, but it is processed. Everybody is familiar with maida, white flour. What is that? That is also wheat, but that is processed. So a feature is something that is processed out of the raw data. So a training data will definitely have the label, which is missed in the raw data, but it will also have some processed information out of the raw data set. There is no necessity that you have to use the raw data set as it is for training. So the answer to that question is, even if you exclude the label aspect, the training data need not be same as raw data. And typically it is not the case. We always try to process some information out of the raw data before we can use it for training. Okay? So that's the basic idea. Okay? So let us look at it from our electrical engineering perspective. Let us consider it's not drawn well, but let us consider that is my current in ampere, and this is time in seconds. Let us say this is the output from a sensor. What features can be generated out of it? So one easy way is, we can generate a peak value, positive peak, negative peak. So that can be considered as a feature. Another thing can be RMS. Another thing can be mean value, right? So you can generate such statistical measures from raw data, and you can use them as features. And this is the features, when put in a vector form along with the label, will form the training data set. So this is what we have as raw data, or original data, or experimental data. We are not going to use this as it is for training. We are going to do data processing. Just like how we convert wheat into suji or semolina, we have to process data and generate feature vector, add label, and use that matrix as our training data set. Okay? One of the biggest advantages of thinking from data perspective is, let us say I have another sensor output which gives me some waveform. So let us say this is voltage. I don't know what is happening, but it's disappearing. The advantage of looking at these in terms of data rather than physical signals is, you can do strange data processing. For example, if I give you 1 ampere current in a numerical example, and if I tell you to add with 10 volts, what will you answer? How will you answer that? You will say this is insane. Like you cannot add current and voltage. They are two different quantities. You will scold me on the exam paper and you will return it, right? But in data is oblivious to all these things. You can actually take a point here on the top waveform and you can take another point on the bottom waveform. You can add them together and consider it as a feature. So once we are looking at it as a data, they are only numbers. You do not have to worry about the physical significance or physical association of those numbers anymore. We prefer to keep it that way. Being engineers, we prefer to have measures like RMS, mean, peak, like that, something that is easy for us to relate or associate with, but there is no necessity. You can do some crazy data processing. Okay? And what you generate is not having any physical association or meaning, but that's okay. We are just using it as a feature. For example, there is something called as a body mass index. Is everybody aware? Body mass index, BMI. So it uses your height and weight, right? And then, so height is in centimeters or meters, weight is in kilogram. But to use to generate body mass index, we have to process these two information, right? So from a data perspective, you can add them together, you can multiply them together. So to calculate body mass index, we are multiplying a kilogram unit, a mass unit, with a meter distance unit. So it's like, okay, so it's kind of a very strange, or adding things like that. Okay. So what I'm trying to say is, once you are into data domain, you have the freedom to manipulate this in any manner you want or you wish. So what does that mean? You have infinite opportunities. So data processing itself is wide open. So once I give you raw data, what should be selected as a feature? There are infinite possibilities. There are many possibilities, right? And how you do that, again, it needs a lot of research. So you can do some trial and error, you can look at literature and you can come up with some ideas. You can come up with your own way of generating features, but there is nothing stopping you from trying it out. Okay? So that is something I want you to be absolutely clear. Some typical features for condition monitoring purposes that are reported in literature for waveforms like current waveform or RMS, mean, peak, root of sum of squares, which is not necessarily RMS, but it's something similar to that. Kurtosis, there is something called as kurtosis. I'll probably talk about it a little bit later. So there are many features. These are features from time domain. But you can also do a frequency spectrum of this current and use the frequency value, the amplitude of that particular frequency value. Okay, you can add two frequency values, amplitude. Such frequency domain features can also be used. So the processing of raw data is completely up to you, and extracting features out of it is completely up to you. What will constitute your training data set given the same original data? So if I give you all the same original data, each of you might generate completely different training data sets. And the machine learning model depends on the training data set, not on the raw data set. So if you are accidentally coming up with an excellent set of training data, your model might outperform every other in this classroom. Okay? So that is the idea, right? So you have to keep that in mind. So how to select features is a question that you need to understand the answer. Okay, so is the general idea clear? So I'm going to start with raw data. We have to do some data processing, generate features. The feature can be multiple quantities. It need not be one quantity. It need not be just RMS, mean, peak, kurtosis, like that. So then feature becomes a vector. I get a label. I stack feature vector and labels one below another. I get my training data set.
So if I take a peak, for example, I'm extracting feature as a peak. Every cycle I will take the peak.
Yes.
So if I have, suppose 1 lakh, my raw data consists of 1 lakh
Cycles.
For example, cycles or I have to convert into cycles. Suppose I am capturing
1 lakh data points.
1 lakh data points, current raw current I am capturing,
Okay.
having 1 lakh data points. So I know how many number of cycles it may be.
Yeah. So the features will be only corresponding to the number of cycles in that case, because what you are doing is a feature that depends on one cycle, right? So it is you will not anymore have 1 lakh data points for that feature. What you will have is only if that 1 lakh has let's say 10,000 cycles, only 10,000 data points
Yes.
as features will be available.
So my feature will have 10,000 data points.
Exactly. So 10,000 rows.
So from that I have to extract and I have to take those.
Exactly. Okay. Is it clear? Like, I do not know if everybody understood the question and if my explanation is clear enough. Okay. So, if,
I have a question.
yes, please.
Fix the features for the, it may be for any application.
Mhm.
Okay. See, here we have some raw data. From the raw data, how to choose the features?
That's a research question, right? So we typically rely on literature. So for example, when I do my work, I will go through literature, what others have tried and what has been reported, if there is any correlation. Say for example, root of sum of squares and root of mean of squares are two different statistical features, but mathematically they are not very different. So you don't have to use them like you cannot you can kind of guess that they are, if one is not going to work, other might not work as well, right? So you kind of have an understanding.
Some people are saying that MS mean square error. Some people are saying that
Error is different. Error, we will not go into that part because we are focusing on a classification problem. So the error will come when we are trying to predict the severity magnitude. So if the severity magnitude, if originally is 40%, and if my algorithm says 38%, then I see an error in prediction value, right? That is the error. So that error we are not bothered at this point. So our whole goal is not to predict severities. We are only restricting ourselves to classifying. Okay. Okay. So we will start with one approach. So this is going to be our first approach. It's a very simplistic approach. As I said, this may not be even considered as a machine learning approach. When I complete it, you will say, is this even machine learning? Probably not, right? But let us get started. So let us consider a training data set which has every feature has two dimensions. That means there are two values for every feature, x and y, or x1 and x2, however you want to call it. And there are two labels, healthy and faulty. All the healthy labels, data points or features, are indicated in blue in color. All the faulty data points are indicated red in color. 1, 2, 3, 4, 5, 6. Okay, 6. Okay, so I have 6 labels. Basically, there is a matrix. So 6 rows corresponding to healthy label, 6 rows corresponding to faulty label. Blue color indicates healthy. So blue means healthy and red means faulty. In fact, I can just use a single letter rather than 2 letters. Okay. So the first approach is, if I get a test data point. So this is the training data set. Okay, so this is my training data set. If I get a test data point, and when I visually plot the test data point, it appears here on the same plane, right? or for the same features. If I ask you to say, take a guess to predict what this test data point would be, whether it's healthy or faulty, what would be your guess? Healthy. Okay, most of you would say that it is healthy, right? Why? Why did you think like that? Okay, so you took proximity. Proximity of what? So the proximity of one data point in the training set, or the proximity of the mean of that class. Okay, so what we are going to start off with is, we will start with one data point. We will see the distance of a test data to its nearest neighbor, or we will try to identify its nearest neighbor. We will calculate the distance. So this is one distance, this is one distance, and this is another distance. It's very clear that this is the shortest distance, and that shortest distance point corresponds to a healthy point from the training data set. Right? So it is like a saying you all would have heard. You tell me about your friends, I will tell about you. Right? So if your test data point is close to healthy, then we say that it should be also healthy. So this is one method you can use to classify. Given a training data set, for simplicity I have chosen 2 features so that I can plot and visually show it to you. It may have 7 features, 10 features, doesn't matter. It may not be captured on a 2-dimensional plot like this, but for sake of ease, I am using 2-dimensional feature vector, and the feature vectors are plotted and the labels are color coded, and when the test point comes, all I have to do is find the distance of this test point with every other point in the training data set. Once I find the distance of a test data point with every other point in the training data set, so what is distance? Usually we will use distance as an Euclidean measure. Under root, if this is a 2-dimensional, let's say x, each of this has x and y, so x training 1 minus x test square plus y training 1 minus y test square under root, right? This is the Euclidean distance. It's a very standard equation. You will be able to calculate the distance using this, right? So is this approach clear? So the first thing is you have to calculate the distance of any given test point to every other point of the training data set. Once the distance is calculated, what do? You have to sort it in the ascending order, in increasing order. The shortest distance will be first, next will be second, and the longest distance will be at the last. So you calculate distance of a test point with every other point in the training data set, then you sort based on distances in ascending order. Then you will look for the label corresponding to the training data set which has the shortest distance to the test point. Okay? So if I write down the approach, so step 1, calculate Euclidean distance. There are different types of distances, so we will use the simplest one for this workshop. Euclidean distance of the test point, or between the test point and every other between the test point and every point or every point of the training data set, Is my handwriting readable? Okay. So you have higher tolerance than I do. I cannot read my own handwriting. Calculate Euclidean distance between the test point and every point of the training data set. Sort based on the data distances. So you get, so imagine this is that, just for clarity, we initially had feature vector, so x, y label, right? So x1, x2 like that, y1, y2 like that. And the label will be either healthy or faulty. It doesn't really matter for us. What we are trying to do is whenever a test point comes, x test comma y test comes, you will calculate the distance with every point, x1 minus x test, or basically the distance between x1 y1 and x test y test, and you will add it here, distance, and you will add it here, okay, a value 1, value 2, like that. And then you will sort the entire matrix based on the last column in ascending order, right? So you will sort based on ascending order. So once this matrix is sorted based on lowest distance will be the topmost row, then what you need to look for is you have to look for the label associated with the shortest distance from the training data set. And you will assign this label to the test data set. So the algorithm is clear, I think. It's not very difficult to think. Okay. So here is an example. So it's for you to do it now. I'm going to give you maybe 6 minutes, 6 to 7 minutes. So I have a training data set. I have labels. I have 2 test points. Follow the approach. Solve. You can discuss, you can work together as a team for this activity. So try to predict the label for the test point 3,8 and 7,1. There are 2 test points. Okay. So maybe we'll give 10 minutes. So I'll give you 10 minutes. Okay. Because I have given both test data points to you same time, it should not take you long. But ideally in real world, each test point will appear sequentially, one after another. So that means you have to rerun the algorithm every time. Okay. But in your case, for the sake of time, I have given you both test points, so you don't have to sort it 2 times. You are going to sort it once, and you are just going to use it. just want to make sure that you have a good grasp on the mathematics. From the lowest value of distance. Is that clear?
First I have to calculate distance in the range.
So take a test point. How far is 3,8 from 7,2? Calculate the distance and enter it. So under root 3 minus 7 square plus 8 minus 2 square. So you get a measure. Enter that here. Likewise 3,8 with respect to 9,3. Calculate the distance, enter the measure. Is the thing clear?
So I'll give you 2 more minutes and then we will go through the distances first.
Review this. So can someone please tell me the values of distances of the test point 3,8 with respect to each of the training points? So 3,8 with respect to 7,2, what is it? 7.74 or 52? Oh, square root of 52, okay. 7.74, okay, good. Or square root of 52. Next one. You can say it's a square root number, that's fine. Root 61, okay. So, root 8 and then root 2. So let me write it as root 52. Okay. So once you have got this, you will do a sorting of this entire table based on the lowest distance to appear as first. So distance to appear as first. So this entry, so after sorting, the table will appear slightly differently. So you will see that the table would have, the topmost row would be 2,9 faulty under root 2. The next row would be 1,10 faulty under root 8 like that. So you will see the table has got rearranged because you have sorted it out. Okay. Then the shortest distance data point, the training data point's label faulty will be assigned to the test data point fault. Okay. So this is the algorithm. Is this clear? Everybody is confident what you have done? Any questions at this point? Okay. So now I am going to ask you, make you do the same exercise. So if you do the same exercise for 7,1, you may get healthy, right? Because of the location. So now I want you to do the same exercise, but the test data point is the same. In the training data set, I got one more data point. I want you to now reanalyze and tell me what is the label of this test data point. Yeah. Just calculate the distance. So we have the distances for everything else. So this is root 52, root 61, root 8, root 2. What is this? Root 1. So now it becomes healthy. Now do you think this is correct compared to the previous one? So if you go into our visual plot form, 3,8, which is the test point, is somewhere here, let's say 3,8. Where is 2,9? 2,9 is a faulty point. 2,9 will be somewhere here. 1,10 somewhere here. Healthy points 9,3, so it is like here. 7,2 somewhere here, right? So when we visually inspect, except for this one point in training data set 3,7, so my 3,7 is somewhere here. I see that the clustering of my faulty data sets and clustering of my healthy data sets, except for one point in the training data set. So typically this could be an error in measurement, what we call as an outlier in our data set. Okay, so someday like the sensor did not work well, you got data which was not correct, and that probably resulted in an outlier point. Now what is the drawback? One outlier point has completely moved my test data point from faulty class into healthy class. Imagine you are in an electric car, your motor data is collected, this is the black point, and because of an outlier, even though there is an eccentric fault, it's being classified as healthy. So you don't send it to the mechanic shop for fixing it. You continue to drive, it might worsen and you might end up having more trouble. Right? So the impact of a single outlier can be disastrous if you are just, this is a very crude, exaggerated example, but nevertheless I want you to understand that when you are just relying on the shortest neighbor or the nearest neighbor, one neighbor, so if I have he may not tell very good things about you, right? But if I ask 10 people, the average might be what is the general perception, right? So one biased opinion might not influence my decision. So the idea here is, rather than going for one neighbor, why can not we do it with multiple neighbors? Okay? So the question is, can I increase from one neighbor to k neighbors? So now this algorithm, this approach is called as k nearest neighbors or k nearest neighbor algorithm, where k is typically greater than 1, but you can always use 1 as well. Your accuracy might be slightly off. Okay? So what can I do? Can I use k is equal to 2? I can use, but what is the problem with using k is equal to 2? Say you want to know about me, you are asking two people. One person says very highly about me, one person says very lowly about me. How will you conclude? Right? You cannot, right? So whenever you use a k, which is an even number, there is a chance of a tied vote. Some people might say faulty, some people might say healthy, and they are equal in number, then we are in trouble. So in k nearest neighbor algorithm, when we want to do classification, we will always use k, which is an odd number. Choose k as an odd number. So k can be 1, next one will be 3. So you ask 3 people. Okay? So for the same example, if you ask 3 people, this is root 1, this is root 2, this is root 8. Am I correct? So if you ask the 3 closest to the test point, 2 will be saying faulty, 1 will be saying healthy. So what will you have to do? You have to vote. Voting is very important. You have to vote as well. In general, I am saying. Okay. So faulty label is outvoting the healthy label. So the assigned value will be assigned label will be faulty, because the majority vote is for faulty. So k nearest neighbor algorithm uses majority vote to decide the prediction of a test point. So in mathematical algorithms, instead of using strings, what you can use is values. Instead of saying h and f, you can say h means 0, f means 1. You can give labels like value zeros and 1, or minus 1 and 1, let's say. You can give some values. So what is majority vote? Is greater than 50%, you know it is on this side. Less than 50%, it is on the other side. Okay? So just doing a simple average will give you majority vote. So this is how typically in implementation you will do. You will not use strings. You can also use strings. There's nothing wrong, but it's easier to use values, zeros and ones. Okay? So now our question comes, how do we choose? How many nearest neighbors should I ask? Can I ask 5 nearest neighbors? If I had asked 5 nearest neighbors, what would have happened? So basically my decision would have changed again, right? So this is not a good example. However, you must keep in mind that choosing k can impact your outcome considerably. And the algorithm itself needs the value of k to be given by you. Any parameter that must be entered into the algorithm by you for it to work is called as hyperparameter. So k is a hyperparameter for this algorithm that you need to specify for the algorithm to give results. So the problem now changes to how to choose k. So I have taken a simple example for the sake of time, but in general what we will be doing is a method. So let us consider a different case. For example, let us say that we have 100 points in the training data set. 100 points in the training data set. So what I will do is I will divide these 100 points into 5-fold like 5 subsets. So I'm going to divide this into 5 subsets. So subset 1, subset 2, subset 3, subset 4, subset 5. I can divide in any, like how do I get, usually they are all equal, okay, equally divided. You can pick the first 20, put it in subset 1, next 20 in pick, or you can randomly pick 20 points and put in subset 1, pick again randomly from the remaining 80 points, 20 points, put in subset 2. It doesn't really matter how you create them, okay. What you will do is, so these subsets are given a name called fold, and what I have created is 5-fold, 5 folds, 5 folds. What I will consider now is, of the 5 folds, I will assume 4 folds as training data and 1 fold as a validation data. So of the 5 folds, 4 folds will be considered as training set and 1 fold will be considered as validation set. See, all are from training data set only, so we know the label for all the 5 folds data, but we are just assuming that one of the folds is considered as validation. What do I mean by validation set? It is a proxy for test data point. So it is going to mimic my test data point. Okay, so what I will do is I will use only 4 folds as training data. I will use a data point from this 5th subset. I will consider that as a test point. I will use k is equal to 1. I will calculate what is the accuracy of prediction. Okay, so let me explain this. So there are 20 points in this set. There are 80 points here, right? So I will pick the first point in this set. So this is my first data point, first test-like point from the validation set. So pick the first point, calculate distance of this first point with 80 points, sort them ascending order based on distances, choose k is equal to 1 and assign label. Okay, so that is, then for the same test data point, choose k is equal to 3, assign label, k is equal to 5, assign label, k is equal to 7, assign label, k is equal to 9, repeat, 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 assign label. Okay? So you can go on until infinity. Okay, so this is for the first. So this is for the first point. Likewise, you will do for all the 20 points. For each of the test point, you will change k from 1, 3, 5, 7, 9, 11 like that. And then you would have got a table, right? So you would have got essentially when k is equal to 1, you would have got some prediction. So what I am going to do is, I am going to draw a plot with k versus accuracy of prediction. The good thing is, because I am using 1 fold from the original training data set, I know my ground truth. So I know how accurately I am predicting in the validation set. Right? So I'm going to predict, capture the accuracy of prediction with different k. So when k is equal to 1, 3, 5, 7, 9, like that. And the general trend you will notice for most of the sets would be the values would tend to increase and then decrease or flatten out. You may not get any more gain by increasing k. So the smallest value of k that gives the highest accuracy in prediction would be chosen. Okay? Okay, does that make sense? So this I have skipped many steps when I explained. So what you have to do is you divide the 100 test points into 20/80. For the 20 points, you are treating them like test points, but you know the ground truth. So you know whether it is actually healthy or faulty, right? But you will not consider the label initially. You will just take it as a test point. You will use the 80 points. You will calculate distances. You will arrange in ascending order. You will first identify label using k is equal to 1. Once arranged in ascending order, you will just say, if I ask only the one nearest neighbor, what will be my label? If I ask 3 nearest neighbor, what will be my label? If I ask 5 nearest neighbor, what is the label? Like that you will do that for the first test point. And then, so when you ask just 1, you may get one outcome. When you ask 3, you may get a different outcome. So you are going to compare it with the ground truth. And you are saying that compared to ground truth, is the prediction correct or not? So you can calculate accuracy of prediction, right? So like that you have to do for all the 20 test points in the validation set by increasing k from 1, 3, 5, 7, 9, 11, 20, like that, increasing to a large value. And then you would have captured the accuracy of prediction and you would plot it with respect to k. And then the value of k that gives the highest accuracy of prediction and lowest number. Say sometimes you can have another plot like this, kind of flattens. So you would probably choose k is equal to 7 rather than 9 or 11, because you do not want to include so many neighbors. You want to just consider fewer neighbors. Okay?
What would be the reason k should be like odd numbers, right?
Okay. Yeah. So if you choose k is even, you may get, because we are doing a binary classification, faulty or healthy, right? If you choose 2, one will say healthy, one will say faulty. So we cannot decide. So that there is a chance of a tie in case of an even number, and we do not want that. There is no super over, unfortunately. Okay, so that's the idea. Okay. So this is using validation set, right? Now in practice, what you will do is you will not just do like this. Rather, see, you have started with 5 subsets. You chose one of them as validation subset and remaining 4 as training subset, right? What you should ideally do is, you should do this 5 times. You should do this entire k selection by running the algorithm 5 times, by considering this as validation set initially, remaining will be training set. Then you will make subset 2 as validation set, the rest would be training set. Subset 3 as validation set, the rest of the 4 would be training set. Validation set, the rest would be training set. Validation set, rest would be training set. So you will have 5 sets of information, and for each of the information you will have a plot like this. You will take the average of the 5 accuracies of prediction for different case, and you will come up with a cumulative end plot. Okay? So this will no longer be just accuracy of prediction from one validation set, but it is the average accuracy of prediction over 5 validation sets. This type of technique is called as 5-fold cross validation. Okay? And then you will pick k. So the algorithm is very simple, but you have to decide on the hyperparameter, and for that you need to do this exercise. Is this clear? Yes, please. You can go beyond 5 too, like 10, 15, 20, doesn't really matter. Ideally, 70-30 would be good for training versus validation. 80-20 is also acceptable. But if you really take a very small percentage for validation, then you are not doing a good job of validation, right? So you want to have at least 20% of the training set to be a validation set.
So if you are considering that 100% is the overall data, actually in that sample algorithm, quiz algorithm, we used to give 70% for the training and the 15% for the
Validation.
and then 15% for the testing. Is it the same kind of rule is applicable over there?
Yeah, that is not a rule, it is just a general approach. So 70% would be used for training and 30% for validation. Test data is completely not at you. Like when you deploy it in a factory, that is when we will get the test data, right? So you don't have access to test data right away.
So that's what we are checking the ground truth value.
So validation set, because it comes from the original training data set, will have a ground truth.
The general rule for this splitting into training and validation is 80-20.
80-20 or 70-30. 70-30, 80-20 is the generally reported split. But there is nothing wrong in going like taking 100 points and dividing it into 10 subsets and doing this. But ideally you do not want the validation to be less than 20%, because you may be just looking at some outliers in the validation set and you may end up with incorrect or inferior accuracy. Okay. So is this clear how to select K? So the algorithm itself looks easy. Selection of K is another problem. So you have to address selection of K first when you are given a data set. Once you have identified K, then only you can go into the algorithm and execute the algorithm. So whenever you are working with K nearest neighbor, what people will ask you to show first is, show me the plot of accuracy of prediction versus K. Or the question would be, how did you choose K? So then you have to show this slide, giving a graph. I ran this, I got this, this is the trend. So the percentage accuracy in prediction does not increase significantly beyond certain K, so I chose that K. Then go into KNN. Okay. So now I think I have given a fair picture of what is K nearest neighbor, right?
If I get 5 plots, average of that plot is average accuracy.
Exactly. Yeah. Usually we wouldn't do 5 plots, we will tabulate them, we will take the average and do one plot, which is the average accuracy of prediction plot. Okay, now comes an application of K nearest neighbor. So I have shared an article with you all for approach 1. So this is basically the results from that article. So what I have done in my lab is I collected 15 seconds of 3-phase line-to-line voltage data of an induction motor. So I supplied an induction motor with the line supply. I collected line-to-line voltage. Since I did this experiment in Canada, our line frequency is 60 Hertz. So the voltage sensor I used is a differential voltage probe with an attenuation factor of 500. That means if line-to-line voltage is 500 volts, the data collected will be 1 volt. Okay? So that is the attenuation factor. I collected this data for 3 different operating conditions and used them for training. So for training, I will talk about training in a moment. So the 3 conditions were when the induction motor had no eccentricity, 20% static eccentricity is one condition. Another condition is 40% dynamic eccentricity. So it's not a mixed eccentric fault, it's just individual faults. Okay? And in all these 3 different fault scenarios, healthy or static or dynamic eccentric faults, the induction motor was operated at no load. That means there was no load coupled to the shaft. And when I collected the data, I sampled my line-to-line voltage at 3600 Hertz. What do I mean by that? So my line frequency is 60 Hertz. So for every period, I am collecting 60 data points. So one sine wave will have 60 data points. Okay? Since I have collected for 15 seconds with sampling frequency of 3600, I have in total 54,000 data points. So this is my raw experimental data that I have got. Okay? This has nothing to do with the training data set or anything, just the experimental data you get. So it may look like this. It's all nice for electrical engineers, waveforms and voltages, and we know that, right? So all these are voltages, line to line, VAB, VBC, VCA, attenuated by a factor of 500. So then my job is features. So what features did I use? I looked into literature. I mean, when I say I, student that worked on it, looked into the literature and decided that the two best features we can use are kurtosis and root of mean of square, RMS. RMS probably closer to electrical engineers, we always try to use that. But kurtosis, so what is kurtosis? It's actually, if you have a normally distributed data, bell-shaped curve, right? So you know how many will be in the tail end compared to in the midpoints or the mean. Compared to a normal distribution, how does your data's distribution look like in the tailing portion of the data set? So how heavily the tails of your data distribution differ from that of the tails of a normal distribution is what we call as kurtosis. If you don't understand this, don't bother too much, because ultimately you will be using an equation to solve for kurtosis. But just to get you perspective, so if you have a distribution of your data set, compare it with a normal distribution how heavily weighted are the tail points of your data. Okay. Now RMS and kurtosis have to be calculated, so we used one period, like one cycle of my wave, to calculate RMS. So I had like 60 points out of the 54,000 points. I need to use 60 points to get one value of RMS. So 900. So these are the equations. So to calculate kurtosis, I do summation I is equal to 1 to n. N would be 60 in this case. Xi minus x bar. X bar is the mean value of that one cycle, which is 60 data points over n, divided by standard deviation to the power 4. Okay. And x RMS is under root I is equal to 1 to n xi square over n. Again, we are looking at 60 points to n is equal to 60 in this. So every cycle I am calculating kurtosis and RMS. And overall I had 54,000 points. So if I divide it by 60, I will have 900 feature vectors per phase. So I have collected 3 line-to-line voltages. So each line-to-line voltage would generate 900 feature vectors of 2 dimensions, kurtosis and RMS. Is it clear? So basically, so the 54,000 data points, if I divide it by 60, I would get 900. So I will take 60 points from the 54,000. For 60 points represents one sinusoidal cycle. So for that one cycle, I will calculate RMS. For the same one cycle, I will also calculate kurtosis using the 2 equations. So every 60 points will give me one feature vector of kurtosis and RMS. Okay. So like that there will be 900 feature vectors, right? And this is corresponding to one line-to-line voltage. I will have VBC, VCA, 3 line-to-line voltages. So I will have a feature vector for line-to-line voltage VAB. I will have kurtosis, RMS. Of course, I will have the label because these are all training data, right? Likewise, I will have for VBC. So there are 1 to 900 in each of them. And then VCA. Is it clear what I have done? Okay, so one thing that I missed to inform you was, once I have calculated the features, before I formed the training set, I made sure that they all had 0 mean. That means my feature vectors, kurtosis, all the kurtosis values, their mean was subtracted from the existing values. So basically it's a data processing. So I shifted the values up or down to have a zero mean for the entire vector. So if this is the kurtosis vector, some values are there, I will calculate the mean of this entire vector, and then I will subtract each data point, the mean from each data point, and the new calculated value is the training data set value. Okay? So feature vectors were normalized to zero mean, means basically they were the mean was calculated and the mean was subtracted from the kurtosis value that was originally calculated. Okay? This way we will have positive and negative values of kurtosis equally spread out. So that's the idea. And because it's two-dimension feature set, kurtosis and RMS only, I could plot them. I have plots for one phase, another phase, another phase, three phase. Right? And I had three training data sets, right? Healthy, static, dynamic. So for each of the data set, I have done the same exercise and I generated the visual plot. Okay. Is the idea clear? Like I'm just following what I said to you. So once this is done, this is my training data set. So I have just represented my training data set visually.
X-axis is kurtosis, y-axis is RMS.
Yeah. So it's just a feature space. You can switch anyway. It doesn't really matter. Is in the yeah.
This is actually, for example, it's one level for a voltage level only we are using. In that itself, we have fixed the features. Am I right?
Yeah, voltage is the data, raw data. From that, we extracted features, kurtosis and RMS. And because I know the ground truth, I know whether this is healthy condition or faulty condition, static or dynamic like that, right? So I could color code it. Okay. So then I have to do my testing. So I chose healthy, 20% static, 40% static, 20% dynamic, 40% dynamic. These are the different operating conditions for which I collected data. I extracted features just like how I did for training data set, kurtosis and RMS, normalized with respect to zero mean. Use that. The only thing I want you to be aware is the healthy might not be at no load condition. It might be at full load condition. So it's just to give difference from the training data set. Okay, so all this let us assume are for full load operating condition. Whereas the training data was generated for no load operating condition. Okay. So the each data set resulted in 900 test points naturally, just like how. And this is how the test points for one of the test data set. Like it is not, there are 5 test data sets, like 5 raw data sets. So I'm not. So the plot is just for one feature vector generated from raw data set. Okay. So now when I look at it visually, because it's 2-dimension, we can conclude saying that okay, this black is closer to blue or red. So it could be healthy or static. It cannot be dynamic. This black is close to blue or red. So it has to be healthy or static. Black is close to green, red. So in this case it can be dynamic or static. But they are all corresponding to the same machine, same operating condition. So what is evident is each voltage, like line-to-line voltages, features extracted out of it might end up giving us different outcomes. So what I did was I used a majority vote based on the outcome predicted by phase line-to-line voltage AB feature set BC CA. So each one predicted, and then I used a majority vote and then I resolved. So if AB predicted static, BC predicted static, and CA predicted dynamic, I would go with static, like that. I mean, it is not a good way to do it when we have 3 classes. Ideally, you should do it when we have just 2 classes. Healthy and faulty, it is easy to do the majority. I also had to do a trick. I had to do an inverse. It's not just a vote, it's a weighted vote. what I did was I weighted vote. Okay, some vote had higher weight than other votes, so that way it helped me come up with that. So this algorithm, when we use k is equal to 1, k is equal to 3 gave highest accuracy of prediction, but k is equal to 1 gave reasonably good accuracy of prediction, more than 90%. Okay. So this is how we implemented k nearest neighbor. So that I have uploaded data set MATLAB files, I think I shared via WhatsApp. So this afternoon during the workshop hours you will be trying to work with the data set. So try to implement. I have given just healthy and static eccentric data set. So try to do a classification. Okay. So you can, that is going to be your afternoon exercise. Okay. I will let you go for tea break using this, using this slide. So what is the advantage of k nearest neighbor in your opinion? Simple, right? So the advantage is simplicity. We all could understand it the first time we heard about it. That's a big thing. But what is the drawback of k nearest neighbor? So if you really think about machine learning, what we want to do is we want to train a mathematical model, but once trained, that mathematical model should be deployable and usable right away. But in k nearest neighbor, there is no such concept of a model. Every time a test point comes, it has to estimate the distance with all the training points. So there is no concept of a model, right? So unfortunately, this is not a machine learning method in the strictest of sense, because no model is actually being generated. Okay? But it's still helpful. It is able to achieve the basic task that we wanted to achieve for our application, and it's very easy to implement and check. Okay? So I will stop here. We'll have 15 minutes break, and then when we meet again, we will go on to next approach. Thank you so much. Little bit time crunch, so we will try to do it. I will try to simplify things, but we are going to enter an interesting territory. Anybody has heard this principal component analysis? So you have, okay, that's good. Anybody has some idea? Much? So do you know what it is, PCA? Can you please tell a few words about PCA? Okay, so what is dimensionality reduction? What are you trying to say?
If you have a large data set with a large number of features in the data set and we want to reduce it to just a few number, or like we want to extract the principal components to it. That data have the features we only want.
Okay, so that's the idea, right? So principal component analysis by definition is intended for intended for dimensionality reduction. Okay, so what do I mean by that? So in the previous example, we had a feature vector comprising of kurtosis and RMS. There were only two dimensions, right? Let us say facial recognition system. There might be many features that have to be included to distinguish whether this person belongs to a particular age or geography or something like that, right? So when the number of features of the feature vector increases, the features can be 10,000, right? So inside a feature vector. So RMS, kurtosis, mean, like that, if you add 100 features, then that is the size of the feature vector. Instead of working with all the features of the feature vector, principal component analysis helps you to work only with the main uncorrelated features within the feature set. Okay, what do I mean by that? So in a feature vector we can have RMS, root mean square. Another feature can be root sum of square. So mathematically, if you see, they would be correlated. Instead of having two such features in the same feature vector, we can eliminate one of them without losing accuracy of prediction. Okay? So principal component analysis is primarily intended for dimensionality reduction of the data set's feature vector. That's the primary objective, while preserving the information as much as possible. Okay. And how does it do that? It tries to find new uncorrelated features from the data set, which are called as principal components. Okay. In this example that I am going to show you, we are not going to use PCA in that form or in its original intended purpose. I am just going to use it for classification. Okay. I am not trying to do any dimensionality reduction. That is not my goal. And the reason will be clear when you look at my application. My feature vector will be typically only having 2 dimensions. I can reduce it to 1 dimension if I want, but 2 dimensions is not too many to be bothered about. Okay? So I am not going to be too bothered about dimensionality reduction. I am just going to present to you a general view of principal component analysis. So let us consider data set. So the data set means feature vectors. So let us consider for ease, the feature vector has only 2 dimensions, so I can plot it and visually represent it. One of the first things that you must understand is, whenever we are working with principal component analysis, the data points will be such that they will be centered around the origin. So this is the origin. Actually, I should not have. So around the origin, the data points are centered. So this is an important point to be considered for principal component analysis. So if you do not have a data set like this, what you should do is, you should do centering. So how can you do that? You have to first, given a data set, let us consider a data set where all points are like this. What you will do is, you will first estimate the mean of this given data set, and from each of the data points you will subtract the mean, and you will create a new revised data set, and that will be always centered around the origin. Okay? So the first step in principal component analysis, centering of your data set. Okay? That means making sure that you calculate the mean of the data set and subtract the mean value from every data point of your data set. Okay? So that is the first thing. So let's consider a centered data set like this. Okay? What is a principal component trying to do is, rather than representing the data using these many data points, principal component analysis says, I can represent this data using a line that passes through the origin. What do I mean by that? My data originally had so many purple points, right? 8 purple points. Rather than saying that I will have 8 purple points as my data, I am saying that there is only one line that passes through the origin, and that line is giving me all the 8 points of my data. So as you can see, this line probably hits only one of the 8 data points. The remaining 7 data points are not hit by this line, or the 7 data points do not lie on the line, right? So how can I claim? So, so this is the crux of principal component analysis. What we are saying is, once we have a line passing through the origin that represents the given data points, each of the data points will be modified and its projection on the line so there will be a projection of each of these data points onto this red line, and these projected values will be considered as the new data points. So you have original data points, kurtosis, RMS, like that. But you are drawing a line and you are saying that once this line is drawn, the original data points are no longer going to be used. I am going to take a representative of the original data points that will be situated along this line only. So that is the base of principal component analysis. So we are going to use a representational data point along one line, and these projected points will be my data set or data points of consideration. Okay? And this line is called as the principal component. Is it clear? Like, I mean, this is a basic idea of principal components. Whenever you have original data set, you try to fit a line or draw a line that will have the best of representations. So you can have a line like this, or you can even have a line like this. So let us consider for probably the similar data set or same data set. I will try to draw it as close to this as possible. I can also have another line like this passing through the origin. So the orange line is slightly different than the red line, like as you can see. So then I can have my projections of my purple point onto the orange line. So these are projections. So basically the perpendiculars dropped onto the line. Okay. I will discard the purple points. Once I have my projections, I will use the projections for carrying out all my analysis. Okay. So what I am trying to say is, in principal component analysis, we inherently believe that there is a principal component which is representing all the data points. So for a feature vector of 2 dimensions, see, this is a 2-dimensional feature vector. That is why I have a 2-dimensional plot, right? So x and y, 2 values are there for each of the purple points. So for any d-dimensional feature vector, there will be d number of principal components. So if I have a 2-dimensional feature vector, I should have 2 principal components. Okay, so this is the first principal component that I have drawn. We will see how we can select it. You just believe that this red line or the orange line is the first principal component. Once I have my first principal component, the second principal component extraction is done as follows. What you will do is, you will calculate what is the error between the actual data point and the projection. So you will calculate the error, okay, all these errors. And then in the same, so you will do another plot, but this will have only the errors from the previous diagram. So if everything is considered as an error vector, you will see, let us say this is vector 1, vector 2, vector 3, vector 4, 5, 6, 7, 8. So if this is the origin, vector 1 is oriented like this, vector 2 is oriented like this, vector 3 is oriented like this, vector 4 is oriented like this, vector 5 is oriented like this, right? 6, 7, 8, like that, right? So all the vectors are along this new line. So this direction will become my second principal component. So if I draw another line passing through the origin, and if I do the projections now, the error will almost vanish. Do you understand? So for my given data set, which is two-dimensional in nature because there are only two features, I will have two principal components. The first principal component will be one line passing through the origin. It will result in some errors between the original data point and the representative points which are projected onto the first principal component. When I have the errors plotted, I can come up with my second principal component, and that will almost vanish, eliminate all the errors, right? So it will be along this line. You can still calculate the errors, but it should be very minimal for this vector. So if you have a d-dimensional feature vector, you can get d number of principal components. So from first principal component to second, you will use error plot. From second to third, you will use the error plot that will be obtained from this line. Okay? And third to fourth, subsequent error plots. Is this idea clear? This is what I am trying to convey. So it's a very interesting concept. You are saying that the original data points are not data points of interest. They all can be represented using a points on one line only, which is called as the principal component line or principal component. If there is an error, and if that error is considerable, then we can identify another principal component which will allow for the errors to be accommodated. If there is still some error, there should be another principal component. So if there are d features, there should be a d number of principal components. So invariably, as you increase the number of principal components, the errors will start decreasing. Right? So that is the whole idea. So in this example, very clearly the first line had a lot of error, second line has almost zero error. Because all the error vectors, if I plot here, are along this line, right? So if I draw a line passing through the origin that coincides with that error vector, then the error will be close to zero. So the idea of principal component is something simple.
So if it could be like in second quadrant and then fourth quadrant, like that, this line, whichever you are looking
For the error?
the error line, you actually follow that first and then second quadrant. The dotted line are drawn from third quadrant to first quadrant. Why it can't be from second quadrant to fourth quadrant?
Like this? It can be anywhere.
Yes, can be.
So the first principal component can be anywhere, right? But what we have to look at is, when I draw a line like this, what will be the error? So for each point, the error will be this large. So ideally, your principal component will result in minimal errors. So it is like best fit.
Based on the points you have to take.
Exactly. Okay, so pictorially speaking, it is the best fit for the given data set. So it can be anywhere, but the one that gives a minimum error would be considered as the principal component.
So the error actually, we are taking up the error, actually the first principal component error we are considering, then again the second principal component error should be minimum.
Yes. Okay, I think we will do one step at a time. So let us go one step back. Let's take one data set. Let us consider data points which are centered around the origin. So this is an important requirement for PCA, that the data points are centered around origin. You can draw a line passing through the origin, right? There are infinite lines that are possible for this. But what we are trying to achieve is a line that would give us minimum error. So let's say if I draw a line here, the purpose of drawing a line is that I am assuming that all the data points are on this line only. That is not true, but that is my assumption. How far away am I from my assumption? So if I do a projection of all the data points onto this line, that will give me, and if I add all the distances, that will give me my total error. So this red color line that I originally drew is probably having a higher error than a green color line that I can draw like this. Right? So what is a principal component? Principal component by assumption is a line that has all the data points. Since it is not possible, we have to choose a line that gives us the minimum error when the data points are projected onto the line. Okay, so that is the idea of principal components. So that's the principal component. So the first principal component is like this. Once I have drawn the first principal component, then I can estimate the error, projected error. So these distances are projected errors, and if I consider each error as a vector and if I plot them, they will be in one direction, right? Because it's a two-dimensional plot, you will get only one more dimension left. So they will be along one dimension, and that you can now draw a second principal component line which will be along the error vector direction, and that will kind of be the second principal component. If you had d dimensions, even after second principal component, you will see some points will have to be projected and there will still some error exist, and you have to repeat that exercise. So for any d feature vector, d dimensional feature vector, there will be d number of principal components. As you go towards the dth principal component, the error vector will start decreasing. From compared to first to the dth principal component, the error vector should decrease. That's the basic idea. Okay? So is this clear? So this is the basic idea. So we are making an assumption that the given data points are along one line or along a set of principal components only. Okay. Since dimensionality reduction is not my goal, I am not going to focus on that. But if you really want to do dimensionality reduction, then you can see how certain principal components will be more important than certain other principal components. So if there are d principal components, we can only take the first 5 principal components, and the loss in accuracy of prediction will not be much. Then you can use them. So that is how typically dimensionality reduction is achieved. Okay? Yes, please. It depends on the dimension of your feature vector. So if you have a 2-dimensional feature vector, you have only 2 times. If you have d-dimensional feature vector, you will have to do d times. Or you can pick a number that is smaller than d. If you know ahead of time, after this value, the error will be much smaller and I am ignoring. Minimum value. You will never achieve 0 error. You are just trying to mitigate error. That is the goal. But why I am not too bothered about the mathematics of implementing it this way is because, interestingly, for principal component analysis, we will never use such approach to implement it. In linear algebra, we have something called as covariance matrix. Okay? And there is something called as eigenvectors, eigenvalues of a matrix. So what happens is, given a data set, if x is a feature vector, and that is the data set, so if x1, x2, x3 are different features, right? And if you have multiple rows, so given a data set, you can actually form a covariance matrix for the given data set. So given a data set, one can form a covariance matrix of the data set. Now I had shared, I will show you a web page link in a few slides where you will help you recollect how to construct a covariance matrix. I know all of us have learnt it and forgotten. So you have to relearn it, right? Interestingly, the principal components, the lines that I drew in previous slide, can be obtained from a covariance matrix using this relationship. So the eigenvectors of the covariance matrix are the principal components. So once you can given a data set, you just need the data set to build its covariance matrix. You don't need any other information. Once you have matrix, covariance matrix, so let's say that you have 2 features, right? If number of features in your feature vector is 2, your covariance matrix order will be 2 cross 2. If you have 3 features, it will be 3 cross 3. If you have 100 features, it will be 100 cross 100. So it will be a square matrix. So that is the covariance matrix. So once you have built the covariance matrix using the given data set, that is all you need to build it. You can actually synthesize the eigenvectors of that covariance matrix, and that eigenvectors are nothing but the principal components. The principal component that is most dominant or the most useful one will be the eigenvector which corresponds to the largest eigenvalue. Okay, so these are terminologies you might have heard, right? So when you have a covariance matrix, you can solve for eigenvalues. When you have a square matrix, you can solve for eigenvalues by solving for the characteristic equation. So if I'm not wrong, if A is a matrix, this is the standard equation we will write, right? Lambda is the set eigenvalues, I is an identity matrix. If A is a matrix, the eigenvalues can be obtained by solving this determinant of A minus lambda I equal to 0. So that will give you characteristic equation, solve for it, you get eigenvalues. The eigenvalues can be, let's say 100, 25, 5, 0.5, like that. Different. The number of eigenvalues will match the number of features, right? So if there are 100 features, we are expecting 100 eigenvalues. If there are 2 features, we are expecting 2 eigenvalues. So if you order them from largest eigenvalue to smallest, and for each eigenvalue, if you generate an eigenvector, that eigenvector will be your principal component. Okay? So that is the idea of principal component analysis. So the implementation of principal component analysis is far simpler because of linear algebra based solution. That once given a data set, one can form a covariance matrix. Then the eigenvectors of the covariance matrix ordered based on highest eigenvalue to lowest will be the principal components of that data set. Okay? So those are the lines. So you don't have to do any error calculation or anything like that. Just some matrix manipulation is what is needed. Okay? So I will give you 5 minutes time to quickly recollect covariance matrix. Here is a QR code because you have been using mobile phones yesterday. So I thought it is better to give QR code. So go through this. It's a web page, just a random web page that gives some basic information about covariance matrix information. So it will show you how, given a data set, you can construct the covariance matrix.
I hope you all have recollected covariance matrix formulation. This is something around the blood. But what I'm trying to say is, to form the covariance matrix, all you need is the data set. So if you have, in the previous example when we did GIAN, if I give you feature vector kurtosis and RMS, right? So kurtosis, RMS are two features, so you can form a 2 cross 2 covariance matrix. That should be doable. Like once you have formed the covariance matrix, you will estimate the eigen values of that covariance matrix by solving the standard equation A minus lambda, determinant A minus lambda is equal to 0. A is the covariance matrix, let's say, and lambda is the eigenvalue, I is an identity matrix. For a 2 cross 2 covariance matrix, you will get two solutions for this characteristic equation. If I plot the value of lambda versus the number of eigenvalues, 1, 2, like that, right? This is this high and this is this low. I can say that by ignoring the second eigenvalue, I am not losing much. So if I have a d-dimensional covariance matrix or d-dimensional feature vector, I will have d number of eigenvalues. So if I plot all of them, 2, 3 up to d, and typically their magnitudes reduce, and after some point you will see that the value has become so small, you can discard the last 25 principal components, take only 5 for a 30 dimensional space without losing much in accuracy of prediction. And that is how we achieve dimensionality reduction. So this is the first principal component, the one that has highest order. So you must always plot. Okay, so one thing I missed is, when you are plotting, it is not if you get lambda 1, lambda 2, lambda 3 as solution, you have to first order them based on their magnitude, descending order. So let's say lambda 1 is greater than or equal to lambda 2 is greater than or equal to lambda 3 is greater than or equal to up to lambda d. Then you have to plot and you can decide which eigenvalues you can discard. So the principal components that you will consider should have high enough magnitudes. If all of them have equal magnitudes, then you cannot discard anything. Then all the features are uncorrelated to one another. So all features are equally important. Once you have, let us say, simplified and you want to choose only 3 eigenvalues out of 30, then you can use the standard definition of eigenvector. If x is eigenvector, then the covariance matrix A times x should be equal to lambda times x. You will substitute lambda 1 and you will get first eigenvector x1. You will get substitute lambda 2, second eigenvector. Third eigenvalue, get third eigenvector. So each of the eigenvectors is actually a line in one direction. And invariably all these eigenvectors will be orthogonal to one another. Principal component analysis. So this is the basic idea. So it's a very simplistic method to implement, even though conceptually it's very intense. From an implementation perspective, thanks to matrix manipulation techniques, we can easily implement. So x is a non-zero vector, which gives the direction, and lambda is a scalar, which will attenuate or amplify the vector. So you only work on the magnitude. So lambda is going to increase or decrease a line, whereas x determines the direction of the line.
So greater the magnitude, you have to keep it. Smaller the magnitude, you can discard and you can make an approximation. Okay, so now let us go into our problem, which is fault classification, right? So let us consider an induction motor. So I am going to present two cases. One is for induction motor, one is for synchronous motor. I have acquired, let us say, three-phase currents, IA, IB, IC. These are line currents measured external to the motor, and three line-to-line voltages, VA, VB, VC, VCA, using sensors. So I have three-phase signal, right? Positive phase signals. What I can do is I can apply Clark's transformation. Everybody knows Clark's transformation. Maybe some of you BTech might not know. Okay. So it's a transformation that takes a three-phase system and represent it into two-phase system. Okay. So how will we do that? We use this simple equation. So if you have IA vector, IB vector, IC vector, you do a scalar multiplication of this, like using this transformation matrix, and what you will get is I alpha, I beta. So if you have three sinusoidal waves as shown on the slide on top right, after doing Clark's transformation, you will get two sinusoidal waves which are in quadrature to one another. Right? 90 degrees apart. So the principal component analysis will be done on alpha and beta vectors. So my alpha and beta are the feature data set basically. So I am going to use them to carry out my principal component analysis. So I measured line currents, I transformed into alpha beta domain, and I am using I alpha and I beta to carry out principal component analysis. So what will I do? I will first center the data. I alpha, I will calculate the mean of alpha vector, subtract the mean of beta vector, subtract the mean. I will center the data. Then I will calculate covariance matrix. Then I will calculate eigenvalue. Then I will calculate eigenvector. Right. So my training data set, basically my I alpha, I beta, for training purposes, were obtained from healthy condition at no load and 20% static eccentric condition at no load. And then I tested 5 different data sets. So I alpha, I beta were extracted from line currents corresponding to healthy condition at 50% of full load, healthy condition at full load, 100% of full load, 20% static eccentricity at 50% of full load, 20% static eccentricity at 100% of full load, 40% static eccentricity at 0% load, that means no. So these are the 5 data sets I use for testing. I can also, so for each of these raw data I extracted line currents, I calculated I alpha, I beta, centered, and I will perform principal components. So I use MATLAB to generate my principal components. So if we plot I alpha versus I beta, like alpha versus beta, you will see a circular plot. Ideally it should be a perfect circle for a sinusoidal current. But because of the harmonics, you will see some distorted blue colored circle. And whenever we had eccentric data, the principal components got shifted. So the principal components of healthy are along these two axes as shown here. So for the healthy vector, I have 2 principal components, they are plotted. For static eccentric fault, the 2 principal components are along these 2 lines. So what I can do is, I can define a threshold vector, which is basically a vector in between healthy and faulty. And I can say that If the value is below threshold, it is faulty. If the value is above threshold, it is healthy. So classification becomes very easy. So this process is much simpler, and the good thing is on voltage data set, line to line voltages, we got 100% classification. Of course, all these things have been tested on very little data, so we cannot be super confident of what we have got already. We have to test it with more data set, and then only we can be certain. So is the idea clear? So all I did was I did Clark transformation. That's the only thing I did. After that, it is only covariance matrix, eigenvalue, eigenvector, transposition, and then classification is done based on generating the principal components. So for synchronous motor, three-phase line currents were captured. I did a frequency spectrum of three-phase of the line, individual line currents, and I picked the sideband frequency components. So based on MMF specific permeance analysis, I know that whenever there is eccentricity, certain sidebands will appear. So I picked the magnitude of sideband frequencies, and then I did an inverse transformation from frequency domain to time domain only for sideband components. So initially I had line current comprising of different harmonics. I did a frequency spectrum, identified the magnitude of certain harmonics, and just for those harmonics I did an inverse frequency transformation to get back time waveform. So now I have time waveform of certain frequency components only. Okay. And then I did alpha beta transformation of those time domain components. And then these are the data sets. There are 10 data sets. So now I have tested at static eccentricity and dynamic eccentricity the same approach. So alpha beta is extracted for a specific harmonic component for each of these data set, and then principal component analysis is being done on the alpha beta currents. And you see that when we use, if Fs is the supply frequency, let's say 60 Hz, when I use the 90 Hz component, which is 1.5 times Fs, I can get very clearly dynamic eccentricity component to be on one side of healthy and static eccentricity to be on the other side of healthy. So it is consistent for, this is at full load, this is at 75% full load, and this is at 60% dynamic eccentricity. So 60% severity or 40% severity, the trend remains the same. Whether we are operating at full load or 75% full load, the trend remains the same. So the mathematics wise, if you are using a tool like MATLAB, there is a PCA function, you can use it, or you can use covariance matrix function and you can do this analysis quickly. So the concept wise, principal component analysis is very intense. For our application, since I am only using two-dimensional feature vector, alpha and beta axis currents, it is very much simplified, and that seems to be giving us a trend in classifying whether the system is healthy or faulty. So this is the idea of applying principal component analysis for the given data set to segregate between a healthy condition and a faulty condition. So I have given MATLAB files of two different scenarios, healthy and static eccentric fault. This afternoon, when you go to the lab, like for afternoon session, whenever that is, please try to implement the two algorithms you got familiarized with today. There is no secret, you just have to implement whatever we learned, right? So I will be there to help you out, but not too much help, little bit of help. So you do the internet search, you do MATLAB command search, that is the best way to learn. Okay. So Start with KNN, that is going to be slightly easier. PCA is also easy, it is just maybe we need some time for you to grasp this. So I will stop here. I think we have 2 or 2 research labs starting in a few minutes, so I don't want to encroach that. So I will stop here for this session. In the afternoon we will meet in the lab. I think after 2:30. Okay. Thank you so much.
Any type of algorithm. you have to do it like for error isolate for today, for error in daily. So it gives space.
Not done so this scale of the tracking.
So we are anytime. I know that you have been spending a lot of time on day and only today. So maybe later on in the workshop we'll try to find time at least PCA. For numbers that is slightly different kind of math. This is one type of mathematics, that other one matrix manipulation. Then therefore matrix and all those things. Of course, MATLAB has default PCA function implementation too, but it's always best